So, aquifers and aquatards. So in this part of water resources, we're going to start talking a little bit about more of where does our groundwater come from. And we have these terms called aquifer and aquatard. So an aquifer is a place where we get our water from. It is just a usable source of drinking water. So for us, an aquifer could be really large if it's for a whole municipality. It doesn't have to be very large to be a useful source of water for, say, a home. So an aquifer's term is it's a useful source of water for whatever use you're going to be using it from a home or from there. If you've ever seen the movie Rango, oh, I should put that on the list too. Rango, that is another movie in which they talk about, it's for the water. That's what an aquifer is for. It's for the water. It's aqua for the water. So it's for the water. The other term that we have is what's called aquatard, or an aquaclude, and this is where it excludes the water, or it slows the water through. So if you poured water through, say, sand, it'll go through very fast. But if you poured water on top of clay, it'll just kind of sit there on top of it. This is what happens inside of rivers, lakes. You have this clay bottom. That clay holds the water in, and so you can have things where even in the subsurface, and we'll be talking more about this, where you're going to be having clay, and that clay acts as an aquatard. Well, this aquatard slows the water from getting into it, but it also cleans up the water. And we'll talk about confined versus unconfined aquifers here, and that becomes a very important part of it. So in this picture here, we have different aquifers. So you don't have to have just one aquifer in an area. You can have multiple aquifers. So you can have what's called an unconfined aquifer, and we'll get more into that. You can see in the next slide, where it's right near the surface of the surface. And then we have an aquatard. It's a low permeable thing, so it's confining. And then we have another aquifer lower down, and then we have another low permeable system. And so we can have this layered system in below the ground surface between us, and so we can put our wells in at different depths. And so we could be sitting right next to each other, and one well could have no water coming out, and the next one next to it could be a flowing artesian well, and because it's based upon the geology of the site. So one of the terms that I mentioned on the last slide was this term unconfined and confined aquifer. So an unconfined aquifer is one that is directly overlain by, underneath it is this aquatard. So right above it is this unconfined aquifer. So why is it called unconfined? Is that there's not a clay layer on the top of it. Whatever rain drops on top of this, it'll immediately go into the aquifer. It is in direct connection with the surface, so in connection with our rivers and lakes. If you drilled a well into it, the water would rise up to wherever the water table is inside of it. It makes it very easy to contamination. So as we pour, say, gasoline on the surface, we'll get into pollution, or you do pesticides and herbicides in your backyard. Well, that will impact how much pollution gets into this unconfined aquifer. So unconfined aquifers are they can be used for drinking water supply, depends on where you are, but they're a little bit more easy to contaminate inside of there. And then we have the term confined aquifer. A confined aquifer, again, is confined on the top and the bottom by, say, clay. So it's getting squeezed into between those. And so it is above and below it is a confining layer, so it's held tightly inside of there. And when we put a well inside of it, the water will then come out of that well, and it will rise to what we call the potentiometric surface. If you take a hydrogeology class, you'll get a lot more into that. But this is called the potentiometric surface. So basically, it's like if you put water and you squeezed it, you pushed on it, and water started coming up a straw. You can push water up. That is what it's doing inside of there. Because it's got this clay layer on the top of it, it's great because it prevents pollution from getting into it. So generally, these confined aquifers are less susceptible to pollution. They can make an artesian well. We'll talk more about artesian wells. It doesn't mean great water quality, but it does mean that the water is under confined situation, so it is good. You have this clay here. So if you did, say, spill gasoline on the top here, the gasoline would get into this clay layer and would get stuck into there, and so it wouldn't come out as fast. So this confined aquifer is a lot of times where we get our water supply from. So water comes through is our permeability and porosity is kind of important terms for this. So porosity is those spaces between the grains. So if we took some sand and we had it in there, there'd be spaces in between all of them. That is porosity. So porosity is those spaces between all the grains, and they could be filled with air or water. So the porosity is just the amount of space that's in there. Permeability is how easy is it for water to flow through it. Okay, so when we start thinking about this, sometimes it gets a little confusing for people because porosity and permeability are different terms and they mean different things, but they kind of sometimes are used interchangeably and they shouldn't. So porosity is just how much space there is between the grains. So say I had a clay and I had a sand, okay, and I had 2 jugs of them, okay? Because the clay particles are so small, that surface area to volume ratio, you guys probably remember from intro science classes and stuff, because they're so small, they have a lot of surface area around each of the grains, okay? So they actually have a lot of porosity. There's a lot of space in between all those little clays in there versus a sand, which has big voids because the sand grains are bigger and they don't stack perfectly on top of each other, so there's space in between them, but it'll actually have less porosity. So a clay versus a sand, a clay will have more porosity, more space in between all the grains than, say, a sand. We do use for general terms, like if I don't know what the porosity really is, I didn't test it and everything, it's about 35%. We just say between 30 and 35% is most porosities in most soils. So sand is usually closer to the 30% and clays can be closer to the 35%. So it's not a big difference, but when we talk about porosity, we really are talking about the space in between the grains. It doesn't have anything to do with how easy it is for water to flow through. Easy for water to flow through is, oh, I changed slides, permeability. Permeability is how easy is it for the water to flow through. So if we have a sand versus a clay, it's easier for water to flow through it. So a clay would have low porosity, a sand would have clay would have high porosity but low permeability. And then a sand would have lower porosity but higher permeability. And then we can get into things like fractured rocks. So say we're in an area where we have solid rock material, we can have very low porosity and low permeability. But if we say fracture the rock and we have cracks inside of the rock, we could have maybe still very low porosity but very fast water flowing through, lots of permeability, because those fractures or those cracks inside of the rock act as just tunnels for all of the water to flow through. So understanding the difference between porosity and permeability is very important, and understanding the difference between those two and how they're interrelated with each other, but different ideas. They both begin with the letter P, but they're very different. So this is actually a very important point, and if you're studying for the exam, this would be something that I would spend some time. Make sure you understand the difference between porosity and permeability. So porosity is just the space. So clays will have high porosity, but they have low permeability. How easy is it for water to flow through? So, and then think about the fractured rocks. So very important concept to get through. Well, how do we measure this whole idea of how easy is it for water to flow through a system? Well, water flows through a system very easily. We call this hydraulic conductivity. It's a function of the water or the fluid that's inside of there. So oil would have a different way of looking at this, but we're only talking about water here. But it's how easy does the conductivity. So we think of like how easy does electricity flow. It's the same concept here, is how easy is it for water to flow through a system. And so this is a function of the geologic material that you have inside of there and the fluid that's flowing through. So salt water, saline water will have different ways of flowing than, say, hydrocarbon. versus fresh water. Well, how do we look at this? This was one of the big things that we did, is we have this term called hydraulic conductivity. And hydraulic conductivity varies over orders of magnitude. So you can have gravel, which would have very high hydraulic conductivity, meaning it's very easy for water to flow through, versus a clay, which will have low hydraulic conductivity inside of there. And then you can have rocks like basalt. It can go from lava flows, where you have these lava tunnels that allows water to flow through very fast, versus unfractured solid rock, which doesn't allow water to flow through it at all. And so you can get them all over the place. What we have here in DeKalb, if you drilled, say, below the ground surface underneath campus, we have about 100 feet of what's called the Tiskawa Till. The glaciers came to this point and kind of stopped here for a long time, and they deposit a lot of clay. We've got about 100 feet of clay. And that 100 feet of clay has what we call low hydraulic conductivity. So it has such a low hydraulic conductivity that it's really hard to actually get through all of that clay and get into that drinking water supply. So we actually have really good materials. The clays that's here is equivalent to what you would find inside of a landfill liner. So really good. So hydraulic conductivity, very important to understand. It's how easy is it for the water to flow through. It's related to permeability. There's equations that relate permeability, porosity, and hydraulic conductivity all together. We're not getting into that in this class, but if you took a hydrogeology class or a groundwater class, you would see the equations that show the interconnection between these. But for this class, understand the difference between porosity, permeability, and then hydraulic conductivity. So what's the difference between hydraulic conductivity and permeability? Well, permeability is just how fast does water flow through. Hydraulic conductivity takes into account the geology, but also the material that is the water itself or the fluid that's flowing through it. So it's not just the porous media, but it's also the material into it. And so they're related to each other, but they're not exactly the same thing. So how does water get into our groundwater systems? Well, it's what we call recharge. It's like recharging your battery on your cell phone. We do the same thing with our aquifers. We recharge. So when we get these major rains, I'm like, yay, I'm recharging the aquifers. It's important for us to do that. So recharge is when it comes from precipitation into our ground. It's recharging our aquifers. So it has to go through the sediments into our water table, into there, and then it discharges into rivers and streams. And so this is how our water gets through into it, and so our discharge point is our rivers and streams or our pumps, but the rain is our recharging. It can be snow. It has to be in a liquid form. So right now, when the snow melts, it turns into a liquid. We recharge our aquifers. We can also we could talk about streams and rivers, and we could talk about out west and the snowpack and how that basically keeps the entire west alive into there. How fast does this recharge occur? You know, we're always looking for the fastest battery that could be recharged and everything. Well, sometimes some other things could recharge very quickly. So recharge can occur from everywhere from a few hours to a few years. And so for some of our deep aquifers, it can take hundreds to hundreds of thousands of years. So the water that we're drinking here in DeKalb is thousands of years old. We talked about Yucca Mountain. We talked about how the water there, how it needed to protect our groundwater resources. It could take very long times in some areas. So if we have things that are surrounded by low permeability clays, we can have it take a very long time. And so depending on how fast it takes, you can get it that water moving into your drinking water supply and know how long it's going to take before maybe pollution gets into it. We can do what's called age dating water. So age dating is where we date water, not have a relationship with water. Well, I do. But I'm full of bad jokes today. Dating water is where we say, well, when was this a raindrop? So how long ago was it? And we can actually do different ways to measure how long ago this was a raindrop. We can use things like carbon-14 dating, but we can also use like the production of CFCs, those carbon fluorocarbons, the things that were destroying the ozone layer. Those got into our drinking water supplies as that water was in there, and so we can say, was this water in the last 50 years? We've got other ways of measuring different types of compounds that's inside of our water, and it can age date our water and tell us how old it is. We can also model it and see, like, if we drop the water here, how long does it take to get into our systems? And so it can take a very long time. So when we talk about groundwater, there really is a relationship between groundwater and surface water. These things are very connected to each other. So you can't say groundwater is separate from surface water and surface water is separate from groundwater. They interact with each other. They are in constant communication with each other, especially in our unconfined aquifer or our shallow aquifers. They will be in communication with each other. So our groundwater is naturally discharged into rivers and streams, and sometimes our rivers and streams feed into our groundwater supply. So we can reverse the flow of some of the groundwater by pumping. So we can put a well in, say right near a river, and we can suck that water out of the river by putting a well like right next to the river. So we can actually see when we turn on a pump, the water levels in, say, rivers or lakes will go down because we're pumping so hard. But in some places, this is the only way to treat water. So say we want to have clean drinking water. We don't want to drink the surface water because it's filled with sediments, dirt, fish, all that other stuff. But if we put a well right next to a river, and we start pumping the water out, we can use that soil that surrounds the river as a giant filter media, and then we can pump that water out. So we can actually have the river feeding in groundwater, and then we're pumping it out for drinking water surface purposes. We can also use, if there's a pollution nearby a river or stream. One of the other things that can happen, say we have over in here we have a gas station that leaks, and we know that the groundwater is flowing towards, say, the local river. Well, we could put in an interceptor well right near the edge of the river and pump that out, and so that gasoline never makes it to our rivers and streams. This happened on the corner of First and Hillcrest. So on that corner there used to be 3 gas stations. Now we're down to 1 gas station. And on one of the gas stations they had a leak, and they used to have a series of wells going from the gas station to the Kishwaukee River to make sure that the gasoline wasn't making it to the river. And so they would have interceptor wells and stop it, and then they cleaned up the gasoline, and so now they've removed all the wells because they didn't need that anymore. But there's this interconnection between our surface water and our drinking water and our groundwater surface water interactions. With that, I am going to stop this lecture. We will get into watersheds and different types of things in our next class period.